Again, welcome all to our third session. I just want to say, to start off, we've had a good few days in the lab. We've been held up by some problems with electronic circuitry. Oddly enough, switches. People have been following our updates from Fusion. We finished this year very long upgrade of our spark gap high voltage, high current switches. And then we ended up with some problems that involved solid state little transistor switches, which you would think would be very easy to solve because these are commercial products. They're not things that we designed ourselves. But it actually takes quite a bit of electronic knowledge, which finally we got assistance from our local Greenbrook electronics store, and they had an expert who came and helped us. And on Friday, I was working on one circuit with John, the person from Greenbrook. Syed was working on another circuit. And within a couple of hours of each other, we got both circuits to work. So that was a good day yesterday. So to turn to the readings that we did today, I suspect that they were a little denser than the previous readings. And if necessary, we'll spend more than 2 hours on them. But let me get to starting off with, obviously, the first reading about Maxwell, Helmholtz, Kelvin, and this less familiar person, Clifford. But the first three struggling to understand the relationship of electromagnetic fields and atoms in the context of the analogy between the mathematical relationship between electromagnetic theory and hydrodynamics. So does anyone want to, now I have to admit that not all of the information about that relationship is present in these readings. So I don't know whether people have some background. If not, we'll have to go into it. But does anyone want to take a crack at what is the relationship between electromagnetism and hydrodynamics that they were so fascinated with in the last quarter of the 19th century?
Well, I think it was vortices, but I can't elaborate any more than that, like the way vortices behave in fluid and in electromagnetic fields, or that the model for fluid vortices worked in electromagnetic field.
Right, and what did they find was, so lines of vorticity in hydrodynamics are just basically the imaginary line that would go through the center, that would go along the axis of rotation of the fluid at any given point. So if you had a straight vortex, like, a drain pipe vortex, which is a straight vortex going straight down, then the axis of that vortex would be the line of vorticity. And what did they find that was mathematically analogous in electromagnetism? Yeah. Brian.
That basically that electric and magnetic fields both follow the same principle.
Well, more specifically, though, what was the line of vorticity analogous to in electromagnetism? Okay.
Is it current?
No, it was the magnetic field direction. So that's what started to fascinate them. Now, what isn't in this reading, and I guess people don't know from other background, is that there are simpler analogies that are very useful. Voltage in electromagnetism, potential, that is directly analogous in hydrodynamics to the height of the water. So if you have a dam, if you think of a dam and water flowing over the top of the dam, the higher the dam, the more energy the water will acquire in going down the front of the dam. That's directly analogous to voltage, which is, the energy that's acquired of every particle going through an electric potential, an electric field. Second of all, current. Well, of course, the very word current comes from currents of water, and current in fluid flow is directly analogous to electric current. So the volume of water flowing past a point is analogous to the amount of current flowing past a given point. And then charge, the amount of charge, is directly analogous to the volume of water. So if you think of a charged object, like the capacitors that we use in our big machine, tiny capacitors that the computer is using, you could say that charge in that capacitor is analogous to the volume of water contained in the reservoir. And these things are very useful when you're talking about electric fields. It's very useful to envision these as basically physical contours, because just like water always flows downhill unless you're pumping it, electricity, the electrons always flow from negative to positive. They're always drawn in the direction of the field line. So that's very simple, direct analogies. Now, what they found, what Helmholtz first discovered mathematically, is that you can go further. These are all essentially electrostatic concepts, but you can go further and mathematically you can define the equivalence of vorticity in hydrodynamics and the direction of the magnetic field. And remember from last time, forces act not point to point in electromagnetism, but they act perpendicular. So that if you have a line of magnetic force and you have a charged particle, that charged particle will interact with the magnetic force field in such a way as to force it to circle around the magnetic field line, just as water circles around the line of vorticity. So people were really fascinated by this because they already knew the atomic theory of matter, evidence for that coming out of chemistry, had been evolving during the 19th century. And while it wasn't indisputable, most scientists believed that atoms were real, that there were tiny particles that were different for each element, and that, for example, the hydrogen atom weighed 1.6 times 10 to the minus 24th grams. So they believed that correctly that they knew the size of these, or at least the mass of these atoms, and that they were fundamental to chemistry and everything based on it, presumably including biology. So what this first reading is about is a summary of the efforts of some of these pioneers in electromagnetism, like Maxwell, in thermodynamics, like Lord Kelvin, William Thompson, to try and say, can we get from this field theory, using this analogy to hydrodynamics, for which now we have this elegant mathematical theory, although it involves a lot of somewhat questionable assumptions about an ideal fluid. Can we develop a vortex theory of atoms? Remember, the idea that objects are made out of vortices didn't originate in the 19th century. It's actually one of the earliest scientific hypotheses we know about, because Anaxagoras, who could be arguably called the first natural scientist, he tried to formulate some idea, obviously it wasn't a mathematical theory, of objects forming out of primordial vortices. So this had a really long history. So let me say as the second question, what did you get out of this section in which, they're describing how this vortex theory evolved? And, especially this author, and that's very interesting, mentioned some of the ideological biases that actually went into this. So does anyone want to describe what they understand of Maxwell and Kelvin's efforts to develop this vortex theory of atoms, and what they think of the author, I forget his name. Oh, I'm sorry, it's her name, Isabel Falconer, making these connections to the ideological questions.
Well, can I just say, I still am struggling to understand why they jumped to the vortex, to vortices, to try to explain atomic model. I can't quite understand from that article, or even from what you just said, Eric, is why that was the channel that they went down, that thought channel.
Does anyone want to answer that question? Yeah.
I thought it was maybe like in general, scientists are trying to like build like a universal model that, like, if you can make the jump from fluid dynamics and like vortex theory, which we have on Earth and can more readily experiment with, and then use that to extrapolate out to atom theory, which we know less about and are less able to manipulate, or like electromagnetic theory in space, then it's would be like beneficial to like make that extrapolation and connection if you can, because then you can understand more about the world.
Right. I mean, what had just happened, right? I mean, we're talking about develops in the 70s and the 80s. And well, last session, we were in the 60s with the development of Maxwell's equations. And what was the thing that was so exciting to scientists at the time, and I think even the general public, about Maxwell's discoveries?
I suppose the vortex characteristic of the whole thing.
Well, I mean, more fundamentally, when Maxwell put forward his equations, and remember, they weren't the 4 equations we know now, they were actually 20. What phenomena was he actually trying to address?
Well, electromagnetic propagation.
Right, which he discovered was
Light.
right. So what was exciting to everyone, I'm sure including Maxwell himself, was that in this stroke, he unified three phenomena, two of which were known to be connected, which is electricity and magnetism, but people weren't sure how. He showed that they are aspects of a single phenomenon, electromagnetism. And he threw in light and the other radiation that subsequently was discovered, the electromagnetic spectrum. So this unification of things that seemed to be disparate was a first step towards what we skip forward to the 21st century has morphed into, or I would say degenerated into, the quest for the theory of everything. But the basic idea is that part of the power of science is to unify with more and more phenomena under more and more powerful generalizations. Because the more phenomena you can unify, the more phenomena presumably you can predict. So his theory, Maxwell's theory of electromagnetism, as we discussed in summary last time, allowed a huge number of predictions of very different phenomena that led very rapidly to enormous technological advances, some of which we haven't discussed yet, like, well, I guess we touched on it, the radio transmission and all of that. So here they had two phenomena that, again, they knew were related. They knew that chemistry created electric currents. The first electric currents that people were able to control came from batteries, which, actually dated back to the discovery of electricity in animals. So they knew that the interaction of atoms could create electricity. But they didn't know. And here, starting with Faraday, the field concept that was developed much further by Maxwell seemed to be explaining a lot of phenomena coherently. And that was based on a continuous something that pervaded space. So here we have atoms that are not continuous, there was obvious evidence that they were separate little particles. Again, a hypothesis dating back to antiquity, Democritus, and so on. So how do you put together these very different things? Discrete particles and a continuous field. So the appeal was, well, we know, and Helmholtz further developed, that there are analogies between the continuous fluids we deal with routinely, actually a mathematical idealization of these continuous fluids, and these electromagnetic fields. Fluids form vortices, so therefore, why can't we use this great mathematics that has just been developed to unify these two very different phenomena and basically say, well, there are no particles. These particles are really stable vortices. Excuse me. So they're either vortex rings, like smoke rings, or there's something more complicated. There were theories that they were actually vortex knots, and that the different atoms corresponded to different varieties of knots, because already in the 19th century, mathematicians were looking at the very practical problem of how things get knotted together. So that was the basic motivation for this, was on the one hand, the natural scientific motivation to expand the theory to cover more phenomena. And the other side, which we'll get into much more in the 20th century, the sort of mathematical urge to say, oh, we've got this wonderful mathematical theory, as Alfvén once put it, it's such a beautiful theory, certainly God would use it to create the universe with. So we're getting sort of the first hints of the theory of mathematical beauty. Does that sort of answer your question, Peter?
Yeah, it does. Thank you.
The other thing, the other motivation is, what does Falconer say about how Maxwell and the other scientists actually viewed what a satisfactory theory was? In other words, in this period, in the 19th century, did they consider a satisfactory theory to be just a set of mathematical equations like Maxwell's equations? Or did they feel there has to be another element?
Well, we'll go back to the scientific method and experimentation to prove or disprove.
Right, of course, they certainly believed in that, and they were looking for ways to test this vortex theory. But in terms of the theory itself, what was the other element that a theory should have other than the mathematical equations?
I think it has to be based on something real, something you can touch, taste, or smell. It's not some sort of imaginary thing. You've got to have an explanation. You've got to have something you can tie it to. And that's why the fluid theory was so good, because you had a physical representation for reality as an incompressible fluid that was, and it fitted all the kind of stuff that they knew. As we say, the voltage and current and resistance all have analogies in fluid flow. And then we also had this idea that in fluids, we could have these permanent vortices. And I've found that fascinating, that vortices in fluids could actually be permanent. They could have incredibly long duration. I would have just assumed any spinning vortice would eventually dissipate, but no.
Well, right. But when we're dealing with mathematical theories, we always have to look at the assumptions that go into, because any math is based on certain axioms. The reason why these were permanent vortices was that they were assuming a dissipationless fluid. In other words, a fluid that had no viscosity. So all real fluids do have finite viscosity, and that's why all real vortices tend to have finite lifetimes. And that was one of the criticisms that Clifford and others put forward, is that it was mathematically easy to deal with this ideal fluid. And there were a lot of practical applications where you could ignore vorticity, where you could ignore dissipation. But they were assuming that there was no dissipation of energy, and that's why they got these permanent vortices. the key thing, and I think, Ron, you're absolutely correct about what Maxwell and others were emphasizing. And I believe this myself, that you cannot understand a physical phenomenon with only a set of equations, that you need an image of a physical process that is occurring that these equations are an exact description of. And that's really something that has somewhat disappeared. And we're going to get into how it disappeared in the 20th century. But you do have the notion that if you can use the equations, then you understand the phenomenon. You don't have to have an image that makes sense. And a lot of people get into this, for example, and we'll see in future classes with quantum mechanics. But that's really not true, because as a practical matter, unless you have that physical image, you can't know how to apply the equations. The equations are just going to sit there. And we at LPPFusion have two personal examples of this. When I met Ivy, whose academic background is computer science, she said that she really knew very little physics. And I said whether she had taken courses, and she said, yeah, she got A's in all the courses, but she got A's because she didn't have any problems. She doesn't have any problems with math. So she memorized the equations, and she used the equations on the exam, and she got all A's. But she had no idea what the equations meant. I guess the teacher was not a very effective teacher. And I had actually a similar experience in graduate school, because after I graduated with a physics degree in from Columbia, I was admitted into a graduate program, PhD program at University of Maryland. And at that time in my personal development, I had thought that I was going to go into what was called particle physics, which now is called high energy physics, fundamental physics, or what have you. Because I had sort of been convinced by the propaganda of the time this was the most exciting field. They were going to discover what underlies the nucleus, what underlies the proton and the electron, just as in the early part of the 20th century, we had shown that the nucleus is composed of neutrons and protons, and we get nuclear energy from that. So I started taking courses in particle physics, and I rapidly concluded that the direction that particle physics was going in was completely wrong and would not lead to any fundamental results, because it lacked any coherent picture of the physical processes. It was simply assumed, and again, I'm skipping forward a little, that these were point particles by definition. But the mathematics that describe particle physics, that describe the application of quantum mechanics to particle physics, was actually very simple, quite simple to understand, the mathematical formulas. And I did the same thing years earlier than Ivy. I memorized the mathematics and I aced the final. But at the end of the year, I concluded I knew nothing about particle physics, and I wasn't sure my professors did either. So at that point, I actually exited from the program and by an indirect route ended up in plasma physics. So Maxwell's desire to say we need a physical model was also motivating these vortex models. But I guess the next question is, you know, and this gets into the second reading, Thompson. What were the problems with this model and why did it not progress? And what were some of the criticisms that were raised at the time?
So one of the things that I read in the article is they applied the bullet theory to the model, and it all kind of fell apart because a bullet trajectory is known over time, and then also with with Thompson's study of cathode ray tubes, that was basically in almost perfect vacuum. The phosphorescence would show up in the absence of anything else, and therefore they're like, well, what is that?
Right. I mean, certainly, as we'll get into it in a moment when we get into Thompson, the electron, the discovery of the electron, which was enormously less massive than the atom, he determined it was 1,700. We now know it's 1,836 times less massive than a proton. That threw the theory completely, this was completely not predicted. But what were some of the other objections? Well, what about this guy, Clifford?
The wave characteristics, or the characteristics, the experiments which are shown to behave in a wave-like manner.
What? I'm sorry, please. Peter, you were speaking?
Oh, I wonder whether you were angling towards the problem of trying to unify the wave characteristics of electromagnetic radiation.
Well, we're having electromagnetic problems with you. I mean, with your transmission. Do you know why? You're breaking up. No. Well, the wave and particle duality, that comes a couple of decades later. But what about this fellow Clifford? What did anybody get out of his criticisms, and what was his approach? First of all, had anybody heard of this guy Clifford before reading this? Yeah, well, me too. So this is something that you learn from preparing classes. So Clifford is obviously a very interesting character who I'd like to learn more about. So as Falconer points out, Clifford, not Einstein, was the first to take Riemann's development of non-Euclidean geometry and say, couldn't we use this to describe phenomena like mass, gravity, electricity, and magnetism? This, of course, is the unified field theory that Einstein sought futilely for during the last 25 years of his life. And so Clifford was speculating about this back when Einstein, I guess, back before Einstein was even born. So I think that's quite interesting. But you see that he was criticizing, and I'm quite sure he was not the only one. He was criticizing the vortex theories from the standpoint that they were jumping way beyond observations. And we'll get into this again much more in the 20th century. So Here were scientists very grounded in the experimental observational method, Kelvin, Maxwell. But what were they doing here? They were taking a mathematical idealization, because Helmholtz, as I say, had to make the mathematics tractable, had eliminated dissipation, which is existent in all real fluids. And they were saying, let's start with this really attractive mathematical model and see whether we can make it work on the observations. And although it's not clear they were even aware of it, this is really a methodological error and is different than what Maxwell was doing in developing Maxwell's equations, which was, he was saying, here is this body of observation. What mathematical description will fit this body of observation? And he had the very recent observation that the constant that related electrostatic and electromagnetic units turned out to be identical within errors to the known speed of light. So he was taking observations and trying to, not only trying, but succeeding in developing an overriding mathematical expression that these observations inspired. With the Helmholtz-inspired vortex, they were taking an idealization from observations, a mathematical model that was not an exact description of observations, but was an abstraction from that, and using that abstraction to go back to a model that could then be tested by observation. So this, to me, this is fascinating because this is really an example of perhaps the first time in the history of physics where you have this conflict that's going to be much more evident in the 20th century between starting from the observations and starting from a very attractive mathematical model. And to a certain extent, the problems that they got into was that they had gone far beyond observations, which were just starting to indicate what the atom was like. But what did people think of Falconer's point that some of these directions were actually theologically motivated? Do people think about that? So maybe I can just, it wasn't a point that was totally emphasized, but let me just go back to the reading.
I thought it was interesting, just so you know, I mean, it's I guess the question was over the origin of all these vortices, right?
Right. So
right.
They were talking in this will have interesting echoes or mirror images in our present day debates about the Big Bang. But this was almost the opposite. They were basically saying, remember that in the late 19th century, nobody in science was thinking of an origin of the universe in time. So that, oh, I'm sorry, somebody has come in late. Hi, Layla?
Yes, I'm so sorry I joined so late.
It's okay. So just to take 2 seconds to catch you up. So we're sort of, we've been talking about the first reading, the one on vortices and atoms in the Maxwellian era. So we're just discussing the author, Isabel Falconer's point that some of the discussions were motivated by philosophical or even theological considerations, not really mathematical or physical. So I was saying in this epoch, nobody in science was talking about a creation of the universe in time. So that, again, we'll get into this more deeply, but this is, of course, in the era where the study of the Earth has been revolutionized by discoveries in geology and by Darwin and Wallace's theory of biological evolution, which also comes out of the 1860s and became an absolutely central point in the intellectual development of the entire society during the last portion of the 19th century, both for good and for not good. But scientists would definitely have, at that point in time, considered any description of the creation of the universe in time as a purely, religious, biblical, unscientific way of looking at things. It was assumed that the universe had existed. But what they were hypothesizing is that these little vortices, which were in dissipationless theory, permanent vortices, the question is, where did they come from? So they had always existed. They had existed permanently, but they didn't evolve out of something else. And in fact, with this dissipationless theory, they could not have evolved out of something else. So that was one of the critiques. And basically, the defenders of the theory, to a certain extent, fell back on theology to say, well, God could have created these particles, in the infinite past. So, again, I'm skipping forward a little because the next section we're going to get into thermodynamics, the development of thermodynamics in the same period, and the conflicts with the evolutionary view of the development of our Earth. But this was, again, this question, if you have this abstract theory where nothing changes, how do you arrive at the universe that we actually see? And so the critics were basically saying, you can't arrive at this unless you're introducing theological concepts, which most scientists of the time were saying shouldn't be allowed. So this, again, is sort of foreshadowing some of the conflicts that we'll see in the in 20th and even 21st century. So I certainly, if I have time, for the moment I don't, if anybody has time, it would be great as a project to look up this guy, Clifford. Evidently, he did not write a lot about his theories and maybe did not develop his theories very much. And he had the misfortune of dying at a very young age. And that may be one of the reasons why none of us have heard of him up to this time. If you look at the history of science and the people who were neglected, a lot of them, like perhaps the best known example is the example in now I'm exemplifying it by forgetting her name. Watson, Crick, as the discoverers of DNA, what woman was left out of that equation? People remember the name of the woman involved? Anyway, she was the woman who did the actual X-ray analysis that led to the
Rosalind, somebody.
what?
Rosalind.
The last name begins with an F.
Franklin.
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 Rosalind Franklin.
Right. So obviously, one of the reasons she was not, she was basically overlooked was her premature death. And I think the same thing might have happened with Clifford. Clifford only lived into his 30s. If you're an artist, dying can be a good career move because your paintings will appreciate greatly in value, but for a scientist, death is not a good career move. Your contributions may get overlooked. So, but anyway, yeah, I think that what we're seeing with this development of the vortex atom was the first example of theory being driven by the mathematical model and moving away from the close association with observation. Just a step away, but enough so that this approach, which actually, when we come all the way to the 21st century, we'll see still has a lot of merit. There's a lot of evidence that vorticity may be of great importance at the level of the nucleus of fundamental processes at that submicroscopic level. But they had moved way ahead of the observations, and that's what got them into trouble. So to get back to the observations, let's go on to the second reading. Well, first of all, before we go on to the second reading, does anyone want to make more comments on this whole Maxwell and Kelvin vortex atom stuff?
Yes, I wanted to comment something. I didn't know what vortices were. And when I started reading, I thought maybe it was a language that I was having trouble understanding. So I went to Wikipedia. I'm like, what the heck is a vortex law? And they had an explanation that they corresponded to a knot theory to explain atoms. And they had some pictures of these strings, right, with different crossings. And it was really strange how different what the internet said and what this paper said. But what I thought was interesting of that knot theory is that string theory is now using those representations of the knots that they thought of so long ago to explain something else. And it's like a circle. Oh, maybe, well, now string theory is coming back to the knots.
Okay. But
yeah, I thought that was interesting how there's a circle.
You weren't familiar with the term vortex in reference to water?
Yeah, I thought vortices were like when you flush the toilet and then it does this.
The whirlpool.
Yes, but I wasn't understanding what they were talking about in the paper. I wasn't.
Okay,
sure.
well, we did briefly go into this at the beginning of today's session. So let me just review. What people found was that there are many useful analogies between electromagnetism and hydrodynamics, the study of fluids. The simplest analogies deal with the basic concepts of voltage, current, and charge. So the analogy is, if you imagine a dam, the height of the dam is analogous to voltage, because just like when water flows over the front of the dam, the amount of energy it requires is proportional to that height of the dam. The amount of energy electrons acquire, or any charged particles, in going through a voltage drop is proportional to the voltage. So voltage and height are analogous. Current obviously comes from the term current of water or current of fluid. So the amount of electricity flowing past a given point is an electric current. Amount of fluid past a given point is obviously the current. The amount of water flowing past a given point is the current of water. So they're analogous. And then charge is analogous to the volume of water in the reservoir. So if you have a capacitor or other electrical storage device, how much charge is in it times the current flowing out of it equals the current flowing out of it times time. And that's the same with a reservoir. You can empty a reservoir in X time with a current of Y, then the amount of water in the reservoir is XY. So charge and volume of water are analogous. So this was already known. What Helmholtz discovered was that there was a fascinating, perhaps deeper mathematical analogy, which is if you abstract from fluids and say that the dissipation, the viscosity, the frictional forces within fluids are zero. So that's not a fluid that really exists in nature. It's an abstraction. And you can derive mathematical formulas. And in those formulas, the behavior of lines of vorticity are the same as the behavior in electromagnetism of magnetic field lines. And a line of vorticity is if you have a spinning fluid and you draw a line at each point that lies along the axis of the fluid at that point, even if it's curved. And that's called a line of vorticity. And just like in a fluid, a line of vorticity forces fluid to flow around it. In electromagnetism, if you have a line of magnetic field, its influence on an electric charge, as we went into a little bit last time, is to force the electric charge to move around it in a circle. So this essential, what was very exciting was he developed a physical model of this rather perplexing way that electricity and magnetism operate at right angles. So the forces are not point to point, but always perpendicular. And he showed that there was a mathematical equivalence. Now, as we'll get into with the second reading, John Thompson, there was one big omission from that analogy between hydrodynamics and electromagnetism. And before I go into it, let me just ask you, was that a little bit clear about the vorticity, Leila?
Wow, yeah, what a great explanation.
It is?
Yes,
Okay.
yes.
Okay.
Yes, the paper.
So the thing that it was missing was charges, actual particulate charges. In other words, you could have a charged fluid, a continuous fluid, but there's no analogy to the individual charges that you have in electricity. And remember, Maxwell's equations are not perfectly symmetric. They include electric charges and electric currents, but they don't include the equivalent of magnetic charges. So from the magnetic standpoint, it's purely a field theory. There are no magnetic charges in nature. And the people who are looking for them are just spending money futilely. And that's what this Vortex initiative was trying to overcome. That could we use permanent vortices that only exist in this abstract dissipationless fluid to model the particles that we knew existed in electromagnetism. So let's just go on to J.J. Thompson, because J.J. Thompson discovered a particle that they didn't even think existed. Now, this became routine in the 20th century, but was quite shocking in the 19th century. And
Can I just comment on the one thing that was interesting and maybe related to what you've said before? It's just the whole conclusion of the paper about sort of the dominance of the most sophisticated mathematical trained scientists over the rest of the scientists. It sort of that gave them a certain authority that they could exploit to push their ideas over those of the more practical minded, I think, or the empirical minded. It just seemed like
the heteronomous mathematics.
It seems like they
That's quite a
took
word.
over people who wanted to look for things in the physical terms.
Right. Does anyone know what heteronomous means? I think it means hegemonic, that this mathematics had hegemony. Yeah, we obviously see this. I mean, again, this is, if you go back to our first session about what is mathematical theory, Alfvén in the 20th century, I think, was one of the leading proponents of a return to a rigorous mathematical theory. And he made fun of the idea that cosmologists could basically dominate the field by saying, you can't understand this unless you can, as he put it, think in 12 dimensions. And if you can't understand this mathematics, which even Einstein actually had trouble learning, then you have no reason to comment. And such sentiments we can't put safely back in the benighted 20th century, because yesterday, I think it was, I heard Dr. Alison Kirkpatrick on a video on recent discoveries in cosmology. I was particularly interested in this video because they happened to be attacking me. But Kirkpatrick was basically saying, if you don't have a PhD in cosmology, you really can't understand what we're talking about and you can't criticize it. And that's what she says to people who come up to her and, on airplanes and say, oh, you're an astrophysicist, what about this? So I think it's a very good point that at that time, hydrodynamics, with this fairly sophisticated mathematical apparatus, had just come into existence. Not many scientists were familiar with it. And yeah, I think it's true that they sort of used this to try and to gain credibility for a theory which did not at that time have a lot of observational backing. Now, it's also true that the people pushing these theory already had enormous prestige because they're very real, solid accomplishments. Maxwell in developing electromagnetic theory, Kelvin and his contributions to thermodynamics, and so on. The reason why we measure temperature in kelvins. Yeah, so that I think that the author makes a very good point. So with Thompson, we're sort of skipping ahead to the 20th century, because even though he made the discovery of the electron in 1897, we're going to say that in physics, the natural division between centuries is really 1895, not 1900. The 20th century started a little early for physics, because starting in 95, you have a series of really astounding discoveries: X-rays, radioactivity, the electron, a number of other things that really were recognized to profoundly change the nature and direction of the study of physics. So, as I say, with Thompson, we're sort of skipping ahead a few months in our sequence, a few years in history. Well, two things. One is transitioning from the last reading. How did the discovery of the electron impact this vortex theory?
Well, for one, it completely, shattered the theory that, the dissipation effect, they thought that the vortices, there was nothing there, and it actually turned out to be that there was indeed something there, a smaller particle of the whole of the atom that became apparent under certain conditions.
Right. This was a huge surprise to everybody, and Thompson himself was greatly surprised when he determined. He was pretty much expecting that the corpuscle would be relevant to the known mass of the atom, and instead it was wildly different. I mean, 1,800 times is not an astronomical number. Physicists deal with much bigger ones, but it is sort of, I would say, roughly speaking, the difference between the mass of an individual and the mass of a blue whale is something of that order. Obviously, we're talking about a particle that was much smaller, certainly smaller in mass, and yet at the identical charge, the two, it turned out had the same charge as the elementary charge in electricity. So, yeah, that was very shocking. What other so what other impact do you think this had at the time?
Well, the other impact that it would have had would have also been the fact that they could reproduce it outside of the cathode ray tube, and determine by the aforementioned mathematical equations when applied to it that it's predominant in everything, not in a controlled environment, but literally everywhere.
Well, but Thompson didn't know that initially. In other words, he just knew that he had discovered this particle that was causing the cathode rays, right?
Right. Yeah, that may have been jumping ahead a little bit, but
Right.
yeah, they basically it caused everybody to look again at, okay, how does this relate to vortices? How what is this? Is this the part of the ether, the undissipatable fluid, or is this something entirely different? Caused them to basically go back to hypothesis and observation again.
Right. So he is writing, you're correct, it's in the reading. He is writing in the Nobel lecture when he received the Nobel Prize for these discoveries in 1906. So by 1906, a decade later, he could say, as you said, Brian, these corpuscles are very widely distributed. They are given out by metals when raised to a red heat. Indeed, any substance gives out corpuscles. And again, corpuscles was his name for what later was called the electron. And that they are emitted by radioactive substances. So again, this is jumping a little ahead as people were trying to pull together the astounding discoveries of this decade that started in 1895. Well, to move on to what Thompson was doing, does anyone want to give a description of how was the electron discovered and how did he determine what its mass was?
Well, I've got a funny answer. He technically was watching TV. I mean, he just didn't know it yet.
Right. And judging from appearances, I would say the vast majority of our class here does remember when televisions were cathode ray tubes. I wonder when. Actually, I can't answer this question.
If you're looking for the first television.
Are those kinds of televisions even sold commercially anymore?
So no, they're not. They ceased production in 1996, 97, was the last ones that were commercially made. I want to say by Toshiba, because this is actually my field. I'm a CEO of an electronics repair corporation. So,
so you get them? Do you get them?
I actually have old ones from let's see, I think the newest one I have is from 89. But I do have another one that's a little bit older from 84.
They can work for a long time because
oh yeah.
My parents bought our first television set in I believe I was 5, yeah, and in 1952. And I think that was replaced in the 1980s.
Yeah,
it functioned for an enormous length of time.
Yeah, the last ones that were made were like the 13-inch ones that had like VCRs or DVDs built in them, sometimes both, on the bigger models, and those were the last ones made like 95, 96, but then everything started going to LCD, LED. I know we're jumping ahead about 100 years here,
yeah, but it is relevant that,
yeah.
Of course, the cathode ray tube itself, which started out as an experimental device, found great application, and until the 1990s was the basic way of conveying visual information electronically in both computers and TVs. So but seriously speaking, does anyone want to describe how he went from cathode ray tubes to cathode rays and corpuscles? Okay. Well, let's see what he said about it in his Nobel lecture. So first of all, he simply blocked. He showed that the rays could be blocked by a simple, a thin piece of metal. So he made, it was in the shape of a Maltese cross, and I'm sorry, it was mica actually. And the phosphorescence, which was the key symptom of the cathode rays, was blocked by this. Then he was able to apply both an electric and a magnetic field. So by applying the electric field, he could see that the direction of movement of the rays was in the direction of the positive field. Remember, up until this moment, no one had known what the charge carrier's own charge was. The reason why electrons are given the negative charge is that people decided historically, on an arbitrary basis, what was positive and what was negative. And it turned out that they were wrong, that the charge carriers had the opposite charge to what they did, but we were stuck with it. So even to this day, we describe currents flowing from positive to negative. With the electrons like trout swimming upstream, no, they're really going in the direction of the field. They are going, of course, from negative to positive, and that's the true direction of the motion of the electrons. Now, currents can be carried by positive charges, by ions. And in fact, in all of our bodies at this moment, most of the currents are being carried by the motion of positive ions. Lots of currents are being carried by positive ions. So simply applying the electric field gave him the knowledge that these were charged particles and that they were negatively charged. When he applied the electric and magnetic field simultaneously, what happened then? Annette, you remember?
Particles moved in circles.
What happens is the force on the electron by the electric field is only a product of the strength of the electric field and the electric charge. But when you put the magnetic field, the bending of the electron depends on its velocity, because we have the force being V cross B. So the velocity and the strength of the B field are both involved. And its mass. So if you take an electric field and a magnetic field, and you adjust the electric and magnetic field so that the forces balance, then you can derive from that what the mass was. So he was able to do this experiment, and that's when he got this very shocking result, that the mass was nothing like the atomic mass, but was 3 orders of magnitude smaller. And that, therefore, the problem had just gotten worse. You didn't just have the electromagnetic and gravitational fields and these little atoms of various types that they already knew was 92 different varieties. Suddenly you had something that was at a qualitatively smaller scale. And this difference really has continued right up to the present day. I mean, even in present day particle theory, and we'll get into some of its limitations, electrons are considered to be elementary particles, and protons and neutrons, which were discovered in later decades to be the constituents that gave the atom its mass, are not considered to be at the same level of simplicity, but they're struck. They obviously have an internal structure. So I would suggest that well, the reason I'm hesitating is I don't know whether to suggest, I'll just throw this out, because I did promise that we wouldn't get too much into the mathematics, but I think that it would be good as an exercise to try and work through what Thompson was determining, because it's a very important experiment, both because of the magnitude of the discovery and because it demonstrated that you could make these fundamental discoveries with fairly simple equipment. And this is something that really pops up again and again in the history of science. In the perspective of the third decade of the 21st century, there is an ideological prejudice that discoveries are made by these gigantic collaborations. I don't know whether anybody has looked at papers in particle physics, but papers in particle physics generally have author lists that go on for pages and pages and pages, because there are thousands of scientists involved in these experiments, and they're done on pieces of equipment that are, CERN, the Hadron Accelerator, the large LHC, Large Hadron Accelerator, is tens of kilometers in diameter. These are colossal pieces of equipment. And you will read the theory of the low-hanging fruit, that, well, those people back in the 19th and early 20th century had it easy. They were making the easy discoveries. We're making the hard discoveries. So give us another $2 billion for a bigger piece of equipment. I think that that's partially misguided. I mean, there's no doubt that some pieces of equipment do take a lot of cost. I mean, I've been excited, and other people have been excited about the discoveries of the James Webb Space Telescope, which is a multi-billion-dollar piece of equipment and really could not have been built for a great deal less. But a lot of scientific progress today is being made with equipment that costs many orders of magnitude less. And that's certainly the case here. So I haven't given any homework. What are people's feelings on homework? Should I give a homework assignment?
Wouldn't be a class if you didn't.
All right, let me see whether I can come up with one. Well, I'm going to give the assignment by email, but basically it's going to be Yeah, basically it's going to be replicate the experiment. I don't expect you to physically do it, but I expect you to describe it and describe how you want to analyze it.
As chance would have it, I actually already did. Do you want to see it?
Well, your homework assignment will be, you're ahead of the game if you've already done the homework assignment, but no, let's wait
Okay,
that for the
I'll
next
wait.
class when other people. Since you're in the business though, Brian, are cathode ray tubes that are not for televisions but suitable for demonstrations, are these a commercial item, like for lab demonstrations?
So, I mean, they're not really readily available. I mean, the more often what you find are going to be cathode rays that were used in like radios.
But they're all coded, you can't see inside them.
Right, and that's the biggest problem is that
Yeah.
sorry, my phone's going off here. There's actually, believe it or not, the best place to find it, something like that is I actually have a guest joining me. He's a little late, but let me finish explaining this real quick. So radio tubes from back in the day, believe it or not, from the 40s and 50s were actually clear. Most of them were made in Germany. So, they might have some unsettling symbols on them. But, you can usually find them on eBay. You can find them on Craigslist. You can find them on, your free and for sale local page on Facebook, that you can use to, basically to whatever ends you want. I'll see if I can procure some. So if people can't actually find them for that, maybe I can ship them out to people. But yeah, most of them
But a
from
radio tube is not exactly the same thing because that has the. So yeah, what we're talking about, again, maybe I see some gray heads here, so maybe people will remember. But I was, as a small child, fascinated by this television, not only by what I could see on it, but when my father was a chemist and felt very competent with all things scientific, he would go into the back, and the back was filled with these orange glowing tubes because that was the technology. Transistors were a thing of the future. And he would have his little tube tester, and when the television turned all static, he'd go in back and he'd test these tubes. And of course, they were glowing because they were transparent. But the tubes had the same function as a transistor, which is to use one signal to alter another signal. So they always had 3 electrodes, while the cathode ray tube basically only had 2, so that electrons, as we now know them, were simply accelerated from one end of the tube to the other, which had the phosphorescent coating. So I think that a lab demonstration might be difficult, but I think it would be worth trying. Brian, maybe we can work something out offline that we could discover that for next.
Yeah, I'll see what's available I can find, and what I mentioned in my email, my buddy Roy here, who's into physics too, he just showed up. So give me a second, we'll be right back on screen here, and he'll be listening. I'll catch him up in the meanwhile after we're done here.
Right. Well, yeah. So I think that it's really important for people to work some of these things out for themselves. And this particularly is such an elegant application of the earlier discoveries of the action of the electric and magnetic fields to make a further discovery, which was the nature and charge and mass of the carrier of electric
Could I
current.
just hop in just for a second?
Yeah.
Because there was something about cathode ray tubes that always fascinated me, and it's kind of important. It was that the way you accelerate the electron is you have a very strong positive charge. That was, I think, called the cathode or the anode. I can never
Now, the
remember.
cathode is, okay, yeah, the terminology is, and I don't
so
know.
one is highly positive.
Anode is positive,
Right.
cathode is negative.
And then what you do
I think
is
the
you
only
heat-
way you can remember it is through this experiment that Thompson discovered the electron. That's
So-
the
so
electron
you-
with the cathode ray, negative.
you heat up the element, and that releases the electrons
Right.
from the surface, which then get accelerated towards the positive charge. Now, what always puzzled me was, all right, you know, I've always been told that electrons and ions, you know, that there's the strongest force there is. So they should just slam together and that should be the end of it. But no, the electrons whiz straight past. All right. So they don't get stopped. And this is, I think, what happens in a plasma, is it not? The fact that, you see, the reason why space is not neutral is because the electrons are moving at the speed of light and they can't just stop on a dime. They don't just go straight and hit the ion and stop. They flash past it. And if they're fast enough, they
Right.
never come back.
Electrons, I mean, in Thompson's experiments, the electrons were moving much slower than the speed of light. Basically, and again, we'll get into this in early 20th century theory and special relativity and E equals mc squared and all that. But an electron is going to be traveling close to the speed of light when its energy gets up to around half an MeV, 500,000 electron volts. Now, the accelerating potentials that Thompson was using, I actually forget them. I don't know whether he says, but they were inevitably only a few thousand volts. And he actually he describes that the velocity varies from approximately 1/3 the speed of light down to about 1/20 the speed of light. And of course, the energy is at these velocities, you can ignore special relativity, and the energies are proportional to the square of the velocity. So, but no matter what the velocity is, the electrons are basically, their trajectory is still governed by good old Newton, which is force equals mass times acceleration, or acceleration equals force over mass. So when they're subject to a force by these powerful electric fields, they travel a trajectory, their acceleration, that is affected by their mass. And even though their mass is extremely small, if they're traveling fast enough, as you say, they're accelerated by the grid, but they're not accelerated so fast that they turn in and hit the grid. So you can imagine acceleration, right, means curvature of a trajectory. So you can imagine as the trajectory comes, their trajectory might be a little curved as they go towards the wire, but they basically zoom on past, just like we recently, everybody was very excited by the interstellar comet, which was attracted gravitationally to our sun, but had so much velocity that it zoomed on fast and said goodbye to us. So,
Excuse me, Eric, I'm sorry. I just have a hard stop. I wanted to say, sorry, goodbye. I'll see you next time and I'll keep an eye for the
okay,
email. Thank
be
you.
on time next time.
Yes, sorry. All
Okay,
right, bye.
okay, bye. So, that again is a good reason for us to try and have a homework about this experiment, because this does deal with the very question of the trajectory of the electrons and how that goes back to the electric and magnetic forces on it.
So Eric, I've been doing a little bit of digging here and seeing what's all available out there for everybody to buy. So I mean, there's a wide variety, like I said, on eBay, and I'm not seeing any DIY kits right as of yet. But the other thing that probably I ought to caution people on too is if we do this for a lab, safety is the #1 priority.
Well, I'm talking about for me,
Oh,
not
okay.
for everybody.
Oh, okay.
Everybody, as I say, I'm going to give a homework description after this. I mean, I'm really busy right now, so it'll probably be a week later. But I should say at this point, since we are talking a little bit about next class, I really think we should say school's out for August and resume in September. People will be going on vacation. And I'm going to have a very big
start.
What?
Universities start too here for me.
Yeah, I'm going to have a very busy August. So I would suggest I'll send out the date, but it will be sometime in early September. But in addition, we're actually, with this third one, we're actually ending a section of the class series, because we're going to go on. We're not leaving electromagnetism permanently, that's for sure, but we are leaving electromagnetism in the 19th century. We're going to go on. The next class will have readings about the development of thermodynamics, which was really the other big development in the second half of the 19th century in terms of physics. But what I would like is sort of a self-assessment from people of what they understand of this basic development of electromagnetism. Because as I say, remember, most of our technology, most of our technology is using today these theories that were developed in the 19th century, 150 years ago. So to understand physics, it's really important to understand these basic concepts. So one of the other things I'm going to ask is a self-assessment, but I'd like it to start in the last few minutes here, is what do people feel they now understand about electromagnetism, about the basic Maxwell's theory of electromagnetism and how it developed? And what do they feel they really don't understand and they need to understand? So I'm going to sort of elaborate on that, have you elaborate on that in writing. But just to get started, I'd like to throw that out. What, anybody can start. What do you feel you do understand as a result of these 3 sessions and the readings? And what do you still need to understand?
Well, I wasn't here for the first two, but I did follow along with the readings. And of course, the field that I work in, I have a very good grasp of these concepts because, obviously if you mix the two in the wrong way, well, yeah, I don't have a job anymore. But yeah, the core concepts of these are used later on, as well as gave birth to later developments. We talked a bit about television and VCRs and DVDs. Those are all interrelated. Yeah, these are very good core concepts for people to understand. Much like I tell people in my industry is like, the reason why I used to work on punch card computers is because that gives rise to allowing me to understand what went wrong in modern day computers. And people sometimes just stare at me with this blank look because they don't even know what a punch card computer is. And I'm like, well, yeah, it makes me understand what's wrong with your computer present day.
Gee, you don't look old enough to have worked on punch card computers.
Why, thank you.
Yeah. Okay. And that,
Okay. From
or
my point of view,
somebody else
I
want to
think-
volunteer?
from my point of view, I think
Go ahead.
electricity, I find, that's sort of understandable. You got protons, electrons, there's physical things there. You've got charge, the charges are different. The problem I have is more with magnetism. I mean, magnetism and electricity are very similar. Magnets have a north pole and a south pole, right? So they attract and repel, but there's nothing there physical that I can understand. I mean, I can see the EM field. Okay, you got an electric field at right angles to a magnetic field, but then how come you can have positive and negative electrical poles, but you can't have a unipolar magnet and stuff like that? Magnetism still seems to me to be the undiscovered country, so to speak.
Well,
So,
what do you what is your understanding of the Faraday and Maxwell notion of the magnetic field being the real object that we're studying? I mean, that was the big breakthrough in 19th century thinking, that we were going from the Newtonian concept of forces acting in an unknown way. He said it in Latin, non fingo hypothesis. I don't make any hypothesis. He didn't care how they were acting, but it was forces between point particles. And the Faraday-Maxwell concept that there is a continuous object that pervades space, which is these fields, the magnetic field and the electric field. Is that something that seems more graspable or still seems totally alien?
Not really, because I can kind of get feels, all right. I did a lot of vector analysis in one part of my life, and I had to get on top of the idea of what a field is, and even then it things make sense until you really, really think hard about something, and then you think, hang on, that there does appear to be a problem at some points with electromagnetism. With the field theories, it is a mathematical description essentially of space, and you posit these electric and magnetic fields. What I'm saying is, for the magnetic side of that, yes, we've got good analogies about what's there. We've got protons and electrons. When we come to the magnetic field, it seems that it's almost recursive. We say, oh, yes, the magnetic field exists because the electric fields in the atoms or whatever. Well, that's kind of a chicken and an egg problem. I can see, because, you know, I guess we've been brought up in the modern age, you know, we understand electricity. Magnetism just still, to me, puzzles me a bit. It's kind of like, if you think about it, there's space is going to have bits which, how do I put this? One way I've tried to think about it is that the magnetic field and the electric fields are incommensurate with one another. They exist in different parts of space, so to speak. I mean, with Maxwell's equation and that, with light, you get the magnetic field is always at right angles or orthogonal to the electric field. So they are somehow related, and yet they're not, because you can't have a magnetic monopole, for instance. So they're not the same things at all.
Well, they're certainly not the same things, but let me go around with other people.
Yeah.
Again, as I say, yeah, how do other people in the class feel about their understanding of these fields? Especially, I mean, I keep coming back to the magnetic field, because the magnetic field is the one that, you know, that was the big discovery, that a field must exist because the action of the magnetic field on electric particles is not this particle to particle. It is always this right angle, the V cross B. So it's something that can't be understood as a particle to particle force. The electric field, you can more or less say, well, it's equivalent to, you have a bunch of particles here, a bunch of particles there. Now, what Maxwell showed was when you have rapidly changing fields, that's no longer true, because you can get an electric field simply with no charges involved, simply by rapidly varying a magnetic field. That's very important to our technology. And I do sympathize with the whole idea that it seems kind of, the idea of fields being physically existing things seems almost, you know, metaphysical. We have people visiting our lab on occasion, especially if they say they want to invest money. And there's the problem of explaining this to people who have no scientific background. And I remember one potential investor asking, how do we get the energy out? And the energy from our device comes out in the form of a beam, and you can use Maxwell's equations to design an inductive coil or other inductive shape so that the beam induces changing magnetic field. The changing magnetic field induces a changing electric field in a coil, and you get electricity out without the beam ever touching anything. And the guy concluded, and this is all based on the same principles that run an electric motor. And the guy concluded, and he said these words, "It sounds like magic to me." He walked out. And so, yeah, so let's just go around the room. We have a few minutes left. Do
No,
magnetic,
I'll go
does,
next.
does the Maxwellian concept of magnetic fields, what you were trying to convey here, sound like magic, or does it sort of make sense?
So I'll go next. Can you hear me?
Yeah.
Okay, so I will just second everything Ron said, and I think you actually articulated a confusing area quite well. I feel like, I guess my mind has just a more natural, intuitive grasp of particles than of fields or waves. And so I can understand this idea of these little electrons that move in a current and create these forces and now fields around them. And the description of magnetism seems almost more like a model or a description of effects that ultimately still come back to these electrons. It is how it seems to me. And so they're more like, magnetism is less of a real thing. I mean, it's real, but it's less of a physical thing and more of an effect that's kind of separately labeled. Is kind of how it feels to me. And then just to move on from that a little bit, like as we have gone through all these different materials, I think I've gotten sort of the big picture story about the whole, dialectic through time of sort of starting with the idea and trying to fit reality to it versus starting with the reality and then trying to find mathematical and models that explain it. And I got the idea that it was really important to technology that you can use electricity to create magnetism and vice versa. And you can use those to create motors and turbines. And that's sort of like central to a lot of our modern technology. But what I guess my problem is that the details don't stick because I don't have enough kind of hands-on experience with how these effects actually play out into stuff that I can observe.
Well, I mean, it comes back, Brian's point about cathode ray tubes is valid. They do involve using high voltages that we don't recommend for everybody. But it does sound like this class could use a lab, and there are a lot of experiments that can be safely done. And hands-on experience in both doing the experiment and interpreting the experiment is pretty much essential. The learning can't be totally mental. So maybe what we're getting from these last things is that Brian is, what is that, Brian? Brian showing something. But before we get to Brian's show and tell, I think, and I'd like a sense of the class, maybe we should not go on to thermodynamics next time, and maybe we should do some lab experiments to try and see whether we can observe the physical reality of the magnetic field, because that's really what people are talking about. Is this simply something hypothesized? I mean, we can't see magnetic fields directly, although we can get pretty close. To be the extreme, and I know nobody believes this, but is this something like dark matter or dark energy, something that, or inflation, something that just physicists have come up with because it's mathematically nuts. The answer is no. Magnetic fields really exist. We have enormous amounts of evidence, and our technology would really not work if magnetic fields weren't a real thing. So I'm suggesting maybe we should try and have a lab next time. Is that possible? And, you know, I think Brian could have some contributions on how we could get some materials together. So what, let me first get a reaction to that. Is that a good idea? Yeah, okay. So what, Brian, what is that you're trying to show us? Because we only have 5 minutes left.
So this is a 40 volt, so basically power supply, and these two big cylinders you see here. So if you imagine the small capacitors you see on boards, these are the larger than life versions of them. This is basically a light emitting diode machine. So the advanced version of, you know, the cathode ray tube, and adjustable between 1 and 28 volts, but you can push it all the way to 40. I just don't recommend it. The number of amps that this will push through here, if you adjust the settings, could kill you about 200 times over. So, but yeah, this is like sort of like the power supply you would need for a cathode ray tube experiment. But I have all sorts of stuff like this around my shop. There was an old guy that came by and he's like, I think you can use these. So there may be something in these boxes we can use.
Right. Well, also, by the way, I may have mentioned we were helped this week by an electronics expert from our local Greenbrook electronics shop. And the shop actually resulted a few years ago of a merger within a family. One shop was owned by a son and one by a father, of a electronic antiques store. So we have some electronic antiques locally available as well. So anyway, I'll try and think about this. As I say, we're going to have a little bit more time because we should push it off to September. But I think that that would be a really good idea to see whether we could come up with some labs with possibly 2 outcomes. One is a more in theory lab, a virtual lab that can do Thompson's experiment, which does involve high voltage, and some real labs that are aimed at observationally testing the hypothesis that the magnetic field is a real process going on in space and is not just a handy theoretical tool. So I'll try and prepare that. As I say, we have some time, so it might be a couple of weeks before you hear from me. Any last comments?
Just going back to your question a few minutes ago
Yeah,
about
sure.
general understanding. I was just thinking, like, it does all like make sense and the story all makes sense. And definitely like working with it and like doing it in a lab, an experiment would help like connecting the dots.
Right.
And then on top of that, I think it still feels like magic a bit.
Yeah.
Like just the fact that it's happening, I feel like is
Yeah.
magic.
Yeah, that's why, yeah, I think that's true. Because, I mean, I was just thinking as we were talking, obviously, at a deep level, science does not completely understand what the electromagnetic field is, because we know from special relativity that you can't have, I mean, if you ask Maxwell what he thought the field was, he would think that it was qualities of this ideal fluid, the ether. And we know, people probably know from their general cultural background, that the ether idea was refuted by the development of special relativity. So in a deep sense, we can say, well, there's still questions. But in a practical sense, I know in working with my equipment, I can't understand my equipment unless I am thinking in terms of an electric field that is a magnetic field that is real, that contains energy, that can not only be acted on, be created, but can act on other things.
Right.
And it's part of what makes our job interesting. It's also part of what makes it difficult. These Maxwell's equations, as I've often said, are easy to write down. Nobody ever said they were easy to solve. Even with a giant computer, they're not easy to solve. So I think that that would be really interesting to basically see what is the process by which people can be convinced that a magnetic field is real. Okay, so we're out of time. So thanks everybody and have a good August. I hope it'll be a relaxing one for everybody, and we'll see you next time.
See you next time.
Thanks.
Take care.
Take
Bye-bye.
care, everybody. Bye-bye.
Thanks, Eric. Cheers.